Okay. Hi, everyone. I'm Masoud Brahman, PhD of Electrical Engineering. And today I want to talk about superposition and quantum realms. That's what I actually do in lab. This is a fraction of a course that I taught for 4 years, advanced quantum mechanics to grad students before. So it's a tiny fraction of it, but it's the most fascinating one because most of the time I use these things that I today want to talk about it in a little unorthodox way, actually, because most of the time my students are familiar with mathematics or something like that. But let's go beyond mathematics and have fun with the actual meaning that we are talking about. And today I want to talk about superposition quantum realm. What I do in my lab is actually something interesting. It's gated tune 2D material as a quantum bits. But if I want to technically talk about it, I can say that it is quasi-quantum dot based on 2D materials to control the quantum states for accurate quantum measurement as a quantum bits for quantum computing. And as you can see, it's lots of quantums. But if you think that we are the persons that use quantum most of the time, you're wrong. There is somebody that used quantum much more than us.
You guys just put the word quantum in front of everything?
Quantum phase, quantum spectrometer, and
Quantum anomaly.
quantum research, quantum entanglement,
Quantum entanglement between the quantum states of quantum technology, quantum energy, quantum system,
quantum healing particle, quantum tunnel,
quantum void.
quantum force. So much quantum realm stuff.
Yeah. Today, I want to talk about so much quantum realm stuff, but in a scientific way, actually, not in the Marvel way, but we use them because they're actually good in it and use lots of quantums in the world, as you see. Okay, let's see what we are talking about. Most of the time, in my when I thought, I start my lecture with this. I said, "Sit tight, and I will tell you a tale like none you could ever heard." And that's true. In order to understand it, we should go back to the history and to see what happens to quantum realms and why quantums become existence. And in order to understand it, we should go back to the world in 19th. Those time was amazing. Most of the peoples gather together, talk to each other, is enjoy, and the realm of science divided into two categories. Most of the people believes that everything that humanity can catch are already found. Lord Kelvin, one of the greats, said that we actually find everything that humanity can get. Anything that we cannot understand is just a little interpretation of a Newtonian law. So, again, we're talking about this guy, Newton. It was a great guy, did lots of things for humanity. Actually, lots of people do lots of things, and Newton's was the gathering all the informations at that time. What did he do? Well, most of us knows the laws of the Newtons and know that if we know all the forces applied to a particle, we can define where it is and where it will go. But nobody talks about it, that's how historical it is important. Before Newtons, before lots of peoples, people gathers with gods. They said, "Oh, Thor, let us have a good something." They prayed for the gods because they cannot predict future. But when Newton's comes, it said that no, the laws on the earth is defined. And if we can predict those laws, we can define exactly what happened in this world. And that's exactly true because we shoot a rocket from Earth and it will reach Mars. We know exactly where it goes, and this is a fact. And actually finding that Jupiter had moons, and those moons follows the Newtonian law, said that the laws of Newton's will apply to Earth and now to the heavens. So all the world act actually based on the law. And in 19s, they believe in that too. Well, we are not sure now. Why? Because we will talk about it, that maybe that is not that true. And those laws may differ from something else. And this is interesting. At that time, they're talking about Newtons, but there is something else too. The waves by this guy, Maxwell, one of the greatest people in electrical engineering, actually, an important one, because he defines the laws of electromagnetics. So at that time, we can define that world divided between these two guys. Well, lots of people talk about wave, but let's consider Maxwell as an denominator for them. So what does Newton said? It said that when an apple and a particle shoots, it follows something, follow a law. And it's those laws applied to particles. But what is particles? Well, something that has mass or something that we can packet for simplicity. And believe me, today's Amazon can pack lots of things. For instance, you can buy an entire house from Amazon and it comes in pack. So yeah, in some case, in the 19th at least perspective, a house is a particle because it has a mass and follows the Newtonian law. And this is true, actually. Another one is wave, something that goes to infinity. You cannot pack it, at least in the 19th way, actually. You cannot pack waves. So you should define this for the first time at the 19th, actually, that something is particle or wave. Okay, then somebody comes and said, how about light? Light is a wave or a particle? This is important. This is important for us to know that light is particle or wave. Because if we know that, we know that use the Newtonian law or the Maxwellian law on it. If it's a wave, Maxwellian law applied. If it's a particle, the Newtonian law applied to it. And actually, Newton himself believed that this is particle. Light is a very tiny particles moving. But lots of other peoples believe in other things, like Ibn Haytham. Ibn Haytham was the father of the optics. We know it as the father of the optics. He, in the original, actually, manuscript, said that maybe it's in a bouncing, something like in a wave. But after that, lots of people come and claim that maybe light is a wave, including Maxwell. So somebody asked, okay, how can we understand that the light is a wave or particle? How can we debate and design an experiment that represents the fact that light is a wave or particle? And this guy comes up. This is Young. He was a great man, actually. He was an archaeologist. And this is bizarre. He can speak 14 different languages, including English, French, Spanish, Portuguese, Greek, Arabic, Persian, and lots of others. He can actually speak 13 dead languages. He was the first person working on a Rosetta Stone. It's a very, very important stone that found to define the hieroglyph. Nobody can read those stuffs until this sand found and this tablet defined it. Actually, the story of the tablet is not important because it's talking about tax, but it's written in 3 different languages and we can actually read Greek. So based on that, they can understand what is hieroglyph, and then we can understand what is the old Egyptian people talks. He, in one of his vacations, found that ducks, when they are moving on water, they create a pattern. And then said, okay, seriously, we can use that pattern to find that something is wave or particle. I said, what? How can you do that? He said, okay, if one wave goes through 2 slides, it creates a fringe situation. Okay, let's see it. Let's see that there is a wave and then going through a slide. Remember, it's one wave going through 2 slides. And as you can see, it creates a fringe patterns near it. And this is interesting. So if wave goes through 2 slides, it creates fringe patterns because wave can do that. It interferes with itself. This is it. Okay. So said, okay, if particle goes through 2 slides, what happens? Let's see. They're using sands. And this is 2 slides. Sands goes through it. Well, We can understand it when sand goes through one slide, it hits the screen and it make it dirty. And then if you do it for a very long time, you can see that two stripes comes out. Let's see. Okay, as you can see, it's two slides near each other. So if something is wave, when it goes through two slides, it will create a pattern like this one, like on the left. And if it's particle, it creates something like that. Well, this is fascinating. Let's go for the light because we want to know what's light doing. So light goes through two slides and then let's see what happens. That's what we are doing here. Remember, it is one light, not two lights, not three, one, just one. And this is important. Okay. And as it goes, here comes the results. The pattern is there. It's not two stripes. It's lots of stripes near each other. It's the pattern. So light is a wave. Well, at least at 19th. This is a great discovery because now we have a solution to distinguish between particle and waves. We said, okay, let's do what the Youngs do. It's the modulation of the Young. So as long as this done and the fringe situation comes out, it's a wave. If not, it's a particle. That's a solid word to define it. Okay, goes on. And when the electrons comes, this guy, J.J. Thomson, find the electrons. Well, he mentioned it as an electron particle. Actually, the name electron comes from electronic ions, means something that carrying charge. And nobody actually believes that now we are electric. We comes from exactly the same patterns. And we are trying to understand the electron, something that found in 1895. Well, at the first, he finds that it has a mass. So name it electron particle. And it's particle. So everybody agrees on that. It's a particle because it's very tiny. It has a mass, actually. So no wave in the world has a mass, at least at that time. So as you can see, it is particle. And everybody believes in that. Then somebody comes and said, okay, I know it's a particle. Everybody knows it's a particle. Actually, it takes 7 years to do something. Somebody comes to that conclusion that, okay, let's do the modulation of the Young, the two-slide experiment, and see what happens. And they did it. They go to electron through two slides. And if it's particle, it hits some places and make it dirty. Oh, make it light, actually. And they did it. Let's see it. Here it's the dirt. You can see blips. And as you can see, I can pack it right there. So it can be packed. It's making dirt, so it's a particle, and everybody happy about it. It was for sometimes everybody said, okay, then somebody comes and said, okay, seriously, let's gather all these dirts, all these blips on each other and see what happens. And they did it. They gathered all these blips and gathered them together on each other. And then something revealed. Let's see what happened. You see? All dirts, all blips. And when they're getting together, what happens? The strips revealed. Now we have a creator, an electron, that both shows the packet situation and the patterns one. And then somebody comes and said, okay, seriously, it cannot be happening. An electron is a particle, it has a mass, it has a dirt. How could it be the electron goes through two slides simultaneously to create something like that? There isn't a problem in the calculations. There is a problem in this experiment. Somebody messed up because an electron as a particle cannot be at two places at once, because if it wants to go both from the left door and the right door, so it should be two actually to do that, to actually goes through both. And remember, it was the wave and one wave, and I absolutely mentioned that it is one wave going through two slides. But now what happens? Both are here. So somebody comes and said, okay, it's a particle. Seriously, we cannot go to some fantasy and said that it's a wave. There is a problem in the calculation. There is a problem in the experiment. And it's a packet. I can pack it. And somebody comes and said, no, it's a fringe situation. It's a wave. Somebody said wave, packet, wave, packet, wave packet. Somebody comes and to understand that electron is wave and particle at the same time and said it wave packet to represent exactly both characteristics. It can pack it, but it creates a wave. And then somebody comes and said, okay, seriously, how can we define it? Because the mathematics is important. And that's exactly the reason this create psi, the wave function or a wave packet, something that represents this characteristic of electrons, both wave and particle at the same time. Remember, at that time electrons did it, and then neutrino said it, and then lots of things shows exactly the same. Everybody mentions that there isn't a problem because it's very tiny. Maybe we create mistakes, but some said, okay, let's go with it, and we consider a wave function for it. Okay, this wave function is a complex function. It's containing a real part and an imaginary part. Let's focus on this a little bit. Real part and imaginary part. It's imaginary. It's the name represents itself. It said I'm imaginary. Well, at least at that time. But now we have something, the electron, that actually shows this imaginary part, something that you can just dream about it. You imagine it is now actually a real part. Actually, it's real. But we cannot understand this imaginary in reality. So somebody comes up and said, okay, we cannot understand this psi because it has some imaginary part. But if, and only if, I multiply it by its conjugate, then I have something that is completely real. And now I can see it in the experiment. And as you can see, they did it. They considered something like this. And what does it represent? But somebody comes and said, okay, when an electron goes through these two slides, I don't know how, and let's consider that the experiment is correct, then it hits some places. I said, yes. I said, okay, where does it hit? The science, since Newton, defined everything exactly. It said that when I shoot a rocket, it will meet the moon. If I target it correctly, it not goes to Vandery. It not goes somewhere that it wants. It exactly goes there. So how the science is this one that we are talking about it? It can hit lots of places. As somebody comes there, okay, no, it's not hit lots of places. It has a probability. Some of them actually hit the center, this part. And most of them did it, 25% of them. 12.5 hits here and here. So we can have some sense that what is the probability of hitting some places? And this is interesting. So this psi, when it becomes real, it shows the probability of hitting some places. But there is a problem in it. Just consider it. You have a car and it's Newtonian. When you brake, what does it do? It brakes, it stopped. It not do something else. It should stop. It must stop, actually, not should, because it's not brake, then catastrophic effect happens. So when you brake the car, it should stop. You said brake and it stop. That's it. But if the car is the quantum realm, then when you hit the brake, is that really? Because it's a probability. 25% of the time it will stop. 25% versus 100%. Come on. That's not science. Because when you can predict that 25% it will break. What is it the 75% others do? Is it go wild? And you said, I have no idea. That's not science. That's exactly the reason Einstein said that quantum is incorrect. It cannot happen, something like that. And the most famous quote of him, God does not play dice because it's random. Well, guess what? God play dice and actually love it. That's a quantum realm. And in quantum, something like this may happen. But this is bizarre. Lots of people cannot understand it, including Einstein and lots of other greats. And they mentioned, okay, we missed something. Either the experiment has a problem, or there is a hidden variable that we have no idea about it. And when we consider that, then the absoluteness will be revealed. We can brake and the car absolutely stopped. And that's a very great situation to consider that. Okay, so everybody again start to debate. Electron is a wave of a particle? Okay, some of people comes to conclusion that we may need some experiment to define it. And one of the greatest experiment that we did is that, okay, if a ball, and a Newtonian ball, shoots to the wall, what happens? It bounces back. It definitely bounces back. And if you're considering something like an anime situation, you hit the ball and it's so strong that will go through the wall, destroy the wall, and goes away. So two options, Newtonian. Either you have so strong that you can shoot a ball and destroy the wall and goes, or it bounces back. So two options is the only case. How about wave? When I'm talking now, does my sounds go through the walls? Yeah, some of them can go. Everybody can hear me outside. And actually, most of the time it's too loud. And so, yeah. Most of the people, when I taught at university, most of my colleagues moved their classes to another side of the country because I shout too much. And well, actually, lots of people will attend that. So, yeah, I'm too loudy. So, my sound and any other situation, X-ray can penetrate through walls. It goes to infinity. It don't care about the wall, at least not this wall. So if I shoot an electron into a wall, or a potential actually, it should bounce back if it's a particle, or it's penetrate through the walls if it's a wave. That's interesting. They did it. And what happens? Well, the electrons bounce back, but then somebody comes from the near room and said, what the hell are you doing? Lots of electrons coming from the wall into my room. So interestingly, electron bounce back and also penetrate through the walls. It cannot be stand here. Now consider your car, the quantum, and you park it in your garage. Tomorrow morning when you comes, it cannot bounce to a wall. It can go whatever it likes to. So it can go to the neighbor's garage without you can even understand it. And that's fascinating, actually, because before that, nothing can go through the walls. Now we have something that can go through the walls. And actually, it's something that Marvel's used most of the time. It's a ghost. It's a substance. Look at her moves. See? It can go through anything it likes because it's in quantum situation. And you can see it. The most beautiful scene is this one. It can go through something and then hit something else. And if you look at exactly this moment that I freeze it, you can see that The electron, the creators, is here, and at the same time is here, and at the same time is here. So you have no idea where does it. And this is important. So everybody comes at, okay, seriously, we are talking about science fiction again. And this is not good. This is not good at all. Because we need absoluteness. Newton's tried hard for that. And we have the absoluteness, and now we don't have it. This is absurd. So somebody said, okay, seriously, we should solve this problem. And how they did it? They said, okay, seriously, we are now goes and consider a situation. And that situation is that scrutinizing the observations that we did. Let's go for a very, very, very precise measurement. And how they did it? Most of the time in the class, I use somebody here and said that, okay, you stand there and we are working together. Now we don't have it, so let's go for it like this. I stand on the two slides and said, okay, electrons comes, I should look at them. If they are going through both slides, I can see it. I said, okay, let's go through two slides. And it goes through right or left, then it's a particle. That's it. And they did it. They stand there, look at it, and remember, I'm looking at it. And my assistant is at the said that's where the electron hits. Okay, let's go. Right, electron goes through the right. My assistant said, right, left, left, right. Remember, I'm just looking at it. I'm looking at the electrons. I'm seeing the apertures. Okay, electron goes through right. My assistant said right, left, left, right, right. And then as long as I'm reading, he said, there is something bizarre here. And said, what is the problem? He said, the fringe situation gone. We cannot see the patterns anymore. The electrons go through the aperture and we can see the patterns, but now it is not creating there. Two slides is creating, it's completely classical. I said, what the hell are you talking about? And I'm not looking at the aperture. And as I'm not looking at the aperture, the creation exists again. The fringe situation comes to exist. But then I said, okay, seriously, it's there. I said, okay, sorry, let's do again. I look, right, left, 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 right, right. Seriously, again, the fringe situation gone. As you can see, there is an experiment about it. If I'm looking at these situations, the electrons go exactly classical. But when we are not looking, they go through both apertures at the same time. So this experiment was coming so that proves that electron is wave or particle, but it makes something add up. It said that electron, we don't know electron is wave or particle. Maybe it's at the same time, it's both at the same time, but they are shy too. When I'm looking at them, they're completely acting normal. But when I'm not looking at them, they go randomly. And this is bizarre. They act as I like. When I look at them, they act exactly like what I want. But when I'm not looking at them, they go randomly to any places they would like to. They go through to both doors simultaneously. And that is fascinating, actually. And this is important, actually. Okay, everybody comes and said, okay, seriously, what the hell is going on? It cannot be happening. It is bizarre. What happens to the side that you're talking about? When you're looking at it, it's becoming some side, and when you're not looking at it, becoming another side? That's impossible. A material is a material. It cannot change. If electrons wants to do something, it do it. It cannot change to something else. So what the hell is going on here? That's exactly the point that somebody comes and said, okay, the wave function that we consider at the first was considering all the possibilities, all the places that can be hit the screen. But now it only hits one place. So the wave function, the psi change, it collapses into an identity that it wants. Let's see it. How does it happen? Okay, this guy goes to quantum realm. And as you can see, everything possibility is there because it can hit lots of places. You see it?
What the hell?
It becomes all the possibility that exists at the same time, at the same moment, all of them. And then they are agreed on something. They are agreed on some identity. Someone looking at them. What happens? All the possibility collapse. And one true identity, maybe. You see? That's the most fascinating thing about the observation effect. All the possibilities exist simultaneously, but when they are agreed on a moment, they collapse into one true identity. And now somebody comes and said, okay, seriously, what happens to the other guys? Those possibilities, lots of them are there, but just one of them become the identity. What happens to the others? Well, somebody comes and said, okay, they disappear. Another one said, okay, it's a hidden variable. Something bizarre is going on there. We are not still finding. That's the question. Another one comes and said, okay, maybe they exist, but not in our reality. Maybe it goes to the parallel world. That's actually the idea of the parallel world. It comes exactly from this moment. Everybody said, okay, the wave function collapsed seriously. Those probability exist. So it cannot collapse to one identity. So when you find one identity, it's in your realm. In another realm, it's another thing. Well, somebody talks about it. Nobody have a proof for that. But it's fascinating for movies. So they're all the time using so much time that some people actually believe that this is true. Maybe it exists, but we have no clue about it. And we are talking about a situation that is now science fiction, but here we are science. I use it in the lab, so it cannot happen in something like this, at least not in this situation that they are talking about it. Okay, so wave collapse function happens, and this is interesting. Okay, in order to understand it better, to make it actually more feeling about it, let's consider a situation. But before that, if there is any questions, you can ask now. Anything. As you can see, we are in the realm of science fiction. So anything that you are thinking about it, it maybe have a proof. Yeah.
So first thing you talked about is about electrons, and then you mentioned the quantum.
Yeah.
And you mentioned the case that the electrons, when it bounces, like when it's going to the wall,
yeah,
some of them will come back, some of them will penetrate.
Yeah.
Is there a way that we can measure the probability?
Yeah. Actually, we can calculate the probability. And actually, tunneling field effect transistors is actually working through the electrons that tunnel through the walls. It's the name represented, tunneling. The tunnels, yes, we can calculate everything about it. We actually, the only thing that is now still debating after 100 years is that how much time it takes that penetrate through the walls. Yeah. If I'm standing exactly at the wall and then use my chronometer to design the time, how much it takes that electrons penetrate through the walls and appear on another side? Is it faster than the light? Or is it not? Nobody knows about it. There is an idea that this goes faster than light because the momentum become imaginary, and this is fascinating. But another person's proof that no, something like that happens. Actually, the last paper published 2 years ago that defined that we have not concluded anything. And the paper published, actually. This is a fascinating one. Yeah. It's yeah. Lots of things happening through these tunneling effects. Any questions? Yeah.
The reason that the electrons can penetrate the wall, is that because of the density difference? Like the electrons so small that it can just travel?
No. If you somebody think about it and then okay, it's creating a wall that is just like the electrons, and still they can penetrate because their momentum become imaginary. So when the momentum become imaginary, you cannot hit it. Yeah, nobody knows. Maybe you would be the one that find the solution that how exactly something like that happens. But when you consider it as a wave, you have a feeling that, okay, seriously, it can happen. But beyond that, no. We are not so sure about it. And in the quantum realms, we are not so sure about anything, actually. And that's the beauty of it. Each day you're in the morning, you see a you see a paper and said, oh, so we have now known that quantum is not working like that. And then tomorrow, another papers and another realms. Feynman once said that anybody said that I know quantum, I have no idea what is quantum, because nobody can understand actually what happens there. But we are seeking. Let's see what happens. Okay. Okay. In order to have a feeling that what just happens in the collapse situation, let's consider situation. Let's consider that UCI and USC have a game together tonight. If I comes to you and said, okay, UCI and Ghost versus Trojans, well, of course we wins. And Anteater, of course, can handle a bit of Trojan. I'm pretty sure the IT guys can handle a Trojan so easily. But let's consider that there isn't a game tonight. And I come to you and said, okay, 50% chance the UCI wins, 50% chance Trojans wins. Let's bet on it. Well, it's a legitimate bet. If UCI wins, I bought you pizza. And if Trojan wins, well, you bought me. That's a legitimate bet, 50% chance. But let's now consider that the game was yesterday. What happens? We already won, but I didn't know that. So I come to you and said, okay, tonight is a game between the UCI and USC. Let's bet on it. And if you are an honest person, you will say, idiot, come on. The game was yesterday. We already won. So what happens to the 50% that Trojan wins? It collapses. Remember, it becomes 100% we win. That's it. So it collapses, actually. So it can be possible that some probability collapse to a reality. But what happens? Is it time? No. If the game postponed for a week, nothing happens. So it's not time dependent. It's game dependent. If the game actually done, if the referee whistled and end the game, the probability lost and a true identity created. So it is based on the game, not the time. It is based on the exam that you did it. In the laboratory, when I examine it, the probability lost and collapse and a true identity become clear. Okay, this is so, the quantum realm is just a simple game that we are playing. Not that simple, actually. Let's consider this situation. Consider there is a game and we are going to bet on it, and it's a 50% chance, 50% chance, 50% UCI wins, 50% Trojans wins. That's okay, that's a legitimate bet. Let's happen, something bizarre happens. They win, we win, okay, we are very happy, they win. Or maybe fog happened. You didn't consider the probability of fogs in your debate. You didn't say if fogs happen, then what we do? It's based on this. We said that if UCI wins, I bought the pizza. If Trojan wins, you bought the pizza. Now fogs happened and the game stopped. So we didn't consider that situation. We should add it up. Next time that we are going, okay, seriously, if I win, if UCI wins, okay, I bought you pizza. If Trojan wins, you bought me pizza. And if fog happens, then I bought a pizza and you bought the, I don't know, the Coke, for instance. That's interesting. How about fire happens? How about when a celebrity comes? How about Batman happens? How about lots of other possibilities? How can I consider all those possibilities? I should think about all of them and add a law about it. But how about in quantum realm? What happens in quantum realm, actually? That's exactly the reason we are going to the wizard world to understand what is the difference between the probability in quantum realm and the probability in classical world. In classical world, you should consider all the possibilities and add something to it. But In quantum, what happens there? In order to understand it, we are going to the world of Harry Potter. Let's see what happens. How many of you saw the movie or read the books? You see the movies. You see the movies? No? Not read the books? Seriously? Okay. In order to actually, this is the third most published book in whole the world. So read it. It's fun, actually. But in order to understand the situation, let's see the movies. This is from the third movie. It's talking about the section that Professor Lupin puts everybody in front of a box. Inside the box, there is a creature that shows and reveal what you're afraid of. Okay? I have a question after this scene. Okay, let's see the scene. It's an interesting scene. It will help out a lot. Okay, Neville is standing in front of the box. When the box opens, well, Professor Snape comes out because he's afraid of Professor Snape.
Ridiculous.
Remember, Professor Snape comes out.
Wonderful, Neville, wonderful, incredible. Okay, to the back, Neville. Anyone form a line?
Now, Rowan is standing in front of him, and all of us knows that Rowan is afraid of spiders. So let's see what happens.
Turn it into something funny. Next. Go on. Concentrate. Be brave.
It turns to a spider. So now the creature is a snake and spider.
One that's ready, one that's ready. Ridiculous. Very good, very good. Marvelous. Absolutely very, very enjoyable. Fantastic.
Now another girl is standing in front of it. And snake. Come on. Now, one and only Harry Potter stand in front of it. The Death Eater comes out. And when Professor stands in front of it, it turns to the moon. Now, I have a question for you. A very important question that can help us understand what is quantum realm.
Sorry about that. That's enough for today. If you'd all like to collect your books from the back of the class, that's the end of the lesson. Thank you. Sorry, Gordon, that's too much for a good thing.
What is the shape of this creature? The name of the creature is Boggart. Boggart is in a folklore English story about something that reveals your what you're afraid of. Now, this creature is inside the box. What is the shape of it? Is it Professor Snape? Is it snake? Is it spider? Is it Death Eater? Is it moon? How wonderful. Somebody afraid of moon. Well, actually, in the 80s, lots of people are afraid of moons, and actually they believe that moons can affect people and make them lunatic. That's exactly the name lunatic comes from Luna. Luna means moon. And actually, if you were in the 18s and 19s and you do some stuff when the moon is full, everybody said, okay, it's being affected by the moon. It was not himself. And the word lunatics comes from that one. So somebody may be afraid of moon at that time, not now, but yeah. Now I have a question. What is the shape of this creature? What is the shape of this boggart? What is it? Nobody can see experiment because as you open the box, you will see the boggart turns to what you're afraid of. So you always measured and see what you want. You cannot see actually what happens there. You can only see what you are, what you're afraid of. That's interesting. Let's for a moment think about it. If I'm an experiment, if I am a scientist and want to do experiment, I said, okay, 50% of the time, 25% of the time, some kind of a snake comes out because humanity afraid of the snakes, 25%. 25%, some kind of scorpion comes out because humanity afraid of scorpions. 10% of the time, a human comes out, different ones actually. But when you ask them, what is your job? He will mention that he is or she is a dentist because 10% of humanity afraid of dentists, 10% afraid of dogs. So you can predict actually what is the probability of opening the box and see, but you cannot actually happening to understand those probability. And remember, these creators consider all the possibilities that you're afraid of. Nobody afraid of moons, but it can turn to moons if you're really afraid of it. So it has the probability to turn to moon. It can have the probability to be Death Eaters. So it has all the cases, not like a computer. You can create something like this with a computer. Yeah, you can use the classical words. How? You can show somebody some pictures and then consider where is which part of the brain is activated, and when the fear part is activated, you said, okay, you're afraid of this one. You can actually create it. But the point is that you must have all these pictures of the world. You should show them. How the hell can I understand that a Death Eaters could be something that you're afraid of? So I'm not considering this in the possibilities. So what happens? I may miss. But in quantum realms, all the possibilities exist. I never accept that some possibilities exist. All the possibilities exist exactly at one moment, all of them. But when you measure it, all those possibilities collapse and become one true identity. That is very fascinating because now if I create a creature that reveals your password, it considers all the passwords in the world, all of them at the same time. And when you open it, the password will reveal, no matter how try you are. No matter how bizarre you create those passwords, you may use I use Oxford Dictionary. Actually, 1, 2, 3, 4, 5, 6. 25% of humanity use that password. I really don't know why, but they use that. So try that one and then start to try other ones. And then you can understand that all those passwords can be revealed. And that's fascinating. And that's exactly what I try to do in my lab. How can I do it? I need a box. This is the box. I need a box to put this creature inside it. I need a quantum realm situation, but as you can see, an electron is inside. And then all the possibilities could be revealed. Any measurements, I open the box, Chicago on the fire. I can open it, and Chicago death, or the flood, or the moon coming to create us, or a lot of different situations. All of them exist exactly at the same time, at the same moment. So the only thing in the laboratory is a box. How can I do it? I do it like this, a Y with the 3 eyes. I apply the voltage and the box created. The electrons goes exactly at this place and trap inside it. Then I can control it how I would like. I never talk about it, that what happens if I put 2 burgers in front of each other. Consider for a moment, just think about it. If I put 2 burgers, 2 creatures that reveals what they're afraid of in front of each other, what happens? Well, that's another story for another day. But as you can see, it could be happenings. And in my laboratory, each day, we do it actually. We put these creatures in front of each other and try to understand what they do. And actually, we measure them in a very different situations to reveal what they try to set us. Well, it's a very hard situations to understand when we are trying to do it at the room temperature. So we need to diminish we need to diminish any distraction. So these electrons trapped here. Remember, I talked and said that electrons can tunnel through the walls. So they can tunnel through this and escape. And actually they did it. So most of the time, the electron comes and before I do any measurement, it's gone. But sometimes in a nanoseconds, I can trap them and I can do the measurements at that specific moment. And that's how can I do what I would love to do. This creature is designed to do as we like. And that's actually quantum dots using for quantum computing. Quantum computing exactly do this. It tries to all the possibilities at the same time, and then the creature something, and then reveal it. It said, okay, all the possibilities at a moment. It never goes through the classical probability. It not goes through when you want to predict your password. It's not going to examine all of them. No, it just collapses to your wave functions. Exactly the wave function collapsed into your password and revealed it. Well, most of the time, actually, it's a probability. So your password is the most probability one, but sometimes it missed. So I do it 50 times, for instance, instead of 50 billion times. That's a huge difference. 50-time experiment versus 50 billion time experiment. That's a huge difference. And that's exactly why quantum computing can do something that all the computers in the world together cannot do in a year. And that's exactly the reason, for instance, IBM give you 12 minutes each month using their quantum computers. And if you are expert, you can use it as long as you like. 12 minutes in quantum realm is a very, very long time. You can do whatever you would like to. Just you need to design the box and you know how to open the box. Because the creator inside is a quantum realm. You should manage it to do as you like. That's another story for another lecture. But today, what I want to say is that quantum objects as the creatures of a particle and wave simultaneously together, and that revealed their properties. All possibilities are exist at the same time, that's named superposition. So an electron goes through two apertures. It can be at two places at once, because that's the probability of them. It can be goes through the right aperture or the left aperture, but at the same time. And that's exactly the reason they can affect on themselves and reveal the fringe situation of the modulation of the Young. Observation collapse the wave function to what you want, and the collapse wave function is the final result. But the big question is, are you sure about it? Thank you very much. And now you can ask questions as long as you like.